This video is going to go through 4 more practice problems. They are all non-calculator again. They actually came from the end of a non-calculator section, so they are going to be some of the ones that may be a little more difficult or a little more abstract. So the first one is completely visual. It wants to know of the functions that are sketched, we were looking for one that is increasing at a decreasing rate. So the first thing I would do is just make sure you have increasing functions. So immediately I'm going to cross off B, D, and E because they're not increasing. Increasing at a decreasing rate means that your first derivative is positive, but your second derivative is negative. So you're actually looking for a function that is increasing and concave down, and that would be C. Another way to think of it is as it's increasing, the increase is becoming more gradual. So the slope is becoming more gradual, whereas letter A would be one that's increasing at an increasing rate because it is increasing and it's becoming more steep. For the next one, we are looking at a differential equation one, and this one is sometimes tough for students because they don't really understand what's being asked. So we have a slope that is defined as 2y over x. So the first thing I'm going to write is that dy dx equals 2y over x. And what it wants to know is, what do we know about the original curve? Is the original curve a line, a parabola, a circle, an ellipse? And the way I'm going to have to do this is I'm going to actually have to integrate it. Before I can integrate it, I have to separate it. So this is a separate and integrate type problem. So what I do to separate it is I'm going to divide by y. So I'm going to get dy over y, and I'm going to multiply by dx. So here is my separated version. The 2, you have flexibility. It could stay where it is, or you could divide by it. You could actually divide by 2y instead of just y. I think it's easier to keep it where it is. We don't have to worry about it as much with the fractions and the logarithm adjustment. When I integrate, I get the natural log of y equals 2 natural log of x plus c. I'm going to make the 2 be the power of x before I clean this up. So I have the natural log of y equals the natural log of x squared plus c. I'm going to take e on both sides. I'm going to exponentiate. And when I do that, the c is going to become the coefficient. So I get y equals c x squared. There is no longer a natural log because the e and the natural log will cancel on both sides. So you actually no longer have an exponential or a logarithmic piece. What that means is your solution is going to have to be a parabola because no matter what c is, it's still going to have an x squared piece, which is a quadratic, which is a parabola. I think the toughest thing about this problem is just knowing what to do from the start. The idea that you have to think of it as the derivative, because that's what slope is, that you have to separate it, that you have to integrate it to get that general solution. Here's an area problem. The challenging part of this area problem, this was actually the second last question, so it was getting to be pretty difficult. The challenging part here is not figuring out area, because we all know that area is just the integral from a to b, top minus bottom. It's figuring out the boundaries and figuring out some of the trig unit circle piece. Because the first thing I would do here is I want to see what these intersection points are. Obviously it starts at 0, but to figure out the other intersection, I have to think about when does the sine of x over 2 equal 0. Well, the sine equals 0, so if you think about your angle, sine equals 0 at pi. But my angle isn't just x, it's x over 2. So we're saying when does x over 2 equal pi? Because the sine of pi equals 0. To figure out what x is, we multiply both sides by 2. So that gives me my boundaries. So the first thing that's challenging is that the boundaries take a little work. The next thing I have to do is I have to integrate. Now, when I do top minus bottom, I don't have to worry about the bottom because it is just 0. So I am just integrating the sine of x over 2. And here comes the second challenging piece, or not really challenging, but easy to forget, is when you integrate it, integral of sine is negative, and you have an adjustment. If you think of your angle as being u, x over 2, the derivative of that is 1/2, so you actually have a times 2 adjustment, and the integral is negative. So you get negative 2 cosine of x over 2 from 0 to 2 pi. And then the last challenging part of it is you have to know your unit circle well enough to put your boundaries in. So you have negative 2 cosine. When I put 2 pi in divided by 2, I get pi, minus a minus 2, so plus 2 cosine of 0. And you can't discount that because the cosine of 0 is not 0. Negative 2 times the cosine of pi is negative 1. So you get negative 2 times negative 1 plus 2 times the cosine of 0 is 1. So you get 2 plus 2, which is 4, which is letter C. So you actually don't end up with pi in your answer because when you take your cosine of it, you get these whole number integer values. tougher problem because of all the little trig pieces that you have to remember. You have to know your unit circle well enough to figure out the boundaries. You have to know your integration and your adjustment, and then you have to know your unit circle well enough to put your boundaries in successfully. And the last problem on this video is a piecewise one. Piecewise is a very common type of question that you'll see on an AP test. And this time the piecewise is actually representing a derivative graph. And it wants to know, if we have this derivative graph, when would the original have a point of inflection? Well, you should know from your curve analysis that if you have a derivative graph, the extrema, the maximums and the minimums, are going to be the place where the original has the point of inflection. The problem is you don't have the graph, so you actually have to come up with it on your own. You have to draw it on your own. So I would come over here and I make a little picture and see what's actually happening with this piecewise function. First thing I'm going to do is check to make sure it's actually, it tells you it's continuous, but I want to see where the one stops and the other one starts. When I put 2 into the top equation, I get 4. When I took 2 in the bottom equation, I get 4. So that's kind of that changing point. That's the point when we switch from a parabola to a line. What this is going to look like, x squared, it's going to be x squared all the way until we get to 2. So from anything 2 and less. So it's going to look like this. 1, 2, 3, 4. I know it's going to stop here. So I'm going to have this parabola that looks like this. And then once I get there, now I'm going to have a line. It's going to be a line that has a slope of a half. So it's going to look something like this. So that is the visual. If they would have just given you that and said, here's the derivative, what are the points of inflection, it would probably be a lot easier problem. You had to create the graph on your own without a calculator. So now, to answer the question, what x values does the original function have a point of inflection, we are looking for extrema. We are looking for places where the derivative goes from decreasing to increasing. So when does the derivative go from decreasing to increasing, or from increasing to decreasing? And it actually only happens once. The only time that happens is right here at the origin, right here at 0. Now you might be tempted to look at this point, and because you do have kind of that sharp point, the idea that you could have a critical value, or in this case a possible point of inflection, but it doesn't switch. It goes from increasing to continuing to increase. The increase is a little bit different. We go from a parabola to a line, but it's still increasing. The derivative didn't change signs. So the only place here where we have that extrema, or that place where the derivative changes signs, is at 0, giving me answer A. All 4 of these questions were on a practice test that were at the end. So you're really looking at questions from about number 20 to number 28 and an end of a non-calculator section. So some of the more challenging ones, not just asking you straight derivatives and integrals.